Hello, my name is Ziwei.
Hi, I'm Yajua.
Today we're going to talk about something uh, about SR models on about epidemics and networks. So epidemic is naturally can be described by a network in the sense that the individuals inside our society can be treated as a node, and the close contact between people can be treated as edge. So in this structure, we can better formulate uh, or simulate the entire process of the propagation of the disease. And on top of that, the SIR model is some model to describe the transmission of the disease. So we believe that combining SIR model and the network structure will be a better choice to precisely simulate the dynamic of the disease. So what is SIR model? SIR model can be simply described as susceptible and infected and recovered. We can divide the total population inside of a country or a community into the three parts. And each part, they have a chance to change the status from one to the next stage. Let's take a susceptible to infected as an example. As we can see that the rate or the number of people to be changed from susceptible to infected people can be described as the gradient of the S, and it's related to the number of population that is infected and also the number of population which is susceptible and times another uh, uh, parameter. Uh, this is very straightforward that if in a city we have more people infected and we have a lot of healthy but a susceptible population, the infected people at the next timestamp will be dramatically boosted given the current setting. And it's the same story for the I and R. So
The SR model discussed in previous slide doesn't incorporate the structure of contact network, which can facilitate the spread of a pathogen. Because we are dealing with networks, we will have a adjacency matrix that describes networks, and we switch from compartmental model to probabilistic model. In this model, each node has a certain probability to be susceptible, infected, or recovered. So these three numbers will add up to 1. So let's look at very simple network. When you do simulation for this network, at each time step, the system has to make a decision whether to infect neighboring node or not. It's a stochastical process. A very interesting observation from SR model is if we are only interested in the distribution of the infection, we actually don't need to simulate the whole process. To make the story short, we can flip a coin for every edge at the very beginning to decide whether it is activated or not. All nodes that are in the activated edge will eventually get infected. Networks play an important role in the infection propagation. Here are some examples where SR model is simulated on different types of networks. If you think about networks here, clearly they will have different ways of infection. For example, if you think about letters network, it will start from some point and it will spread very slowly. While if you think about the scale-free network, when the infection reach a hub, it will infect lots of nodes. So the curves show the result of simulation on different networks. We can see the number of infected people as a function of time. It's obviously that skill-free network has the steepest slope and letters network has the slowest slope. The letters network is a scenario that people aren't compartmented and people are sort of separated and they have minimal interactions. While the skill-free network is very close to the normal social network. So it means we are actually very unfortunately going through the similar fast infection propagation as epidemic will grow very fast. And the only way we can deal with it at this moment is to increase the social distance. And on the other hand, if we have effective vaccine, by removing the high degree nodes, which means vaccinating them, it will have pretty big effects on the disease propagation.
the SR model and networks being together is not only helpful for tracking the propagation of the virus between individual to individual. It's also helpful for keeping record of the dynamic of the contagious inside of a community, province, or even a country. Let's take the Hubei province in China under the COVID-19 setting as an example. So in this map on the left, we can see that each city is labeled by a number, and then each city can be treated as a node inside of the network. And the edge is described by the adjacency matrix, and the value of beta ij in the adjacency matrix describes the probability that a contagious person inside of a city I will pass the virus to another susceptible person inside of the city J.
SR model on networks is still a very hot topic, especially at this moment. There are many open questions in this field. A big problem is the difficulty in obtaining a realistic transmission network. For example, to simulate the spread of COVID-19, it's important to trace the contact, but it's hard for you to accurately remember everyone you contacted. Some papers mention that using smartphone is a good choice to get the network information. And at this special moment, Google and Apple are building such a system that can trace the contacting information. Even though the purpose is a little different, it's still a very useful technology to obtain the realistic network.
So during the time that we dive into this area, we did find a lot of things which are very useful for to know, and also we do find a lot of challenges remaining undone inside of these problems. So as we all know that SR model combined with network is very useful to predict the spread of the pathogen, but it's very hard to know the dynamic of the contact tracing in reality, in the sense that the SR model is very sensitive to the input data, so it requires very high accuracy of the data provided. But however, inside of the real life scenario, the data collected by government or other institutions are not exactly reflecting the true dynamic of the spread of the data, which cause a lot of inaccurate issues to occur. One of the way to solve this is to use the Bluetooth or GPS technologies to keep tracking the social distancing of the individuals and also the infected populations. And another challenge inside of the setting is that SR model is not really enough to simulate some epidemics, for example, COVID-19. Because in the set of COVID-19 settings, some recovered people will have a chance to be infected again. So in that case, we need to some more precise and a complex model to describe the real expressions of the COVID-19. For example, SRS model.